Welcome. You have nothing to do right now, nowhere to be, nothing to remember or plan. Simply let your body settle, let your breath slow, and allow the quiet to hold you. Tonight, we are going to drift together through one of the most beautiful stories the universe has to tell, the life of a star. Let it wash over you like soft light. You can rest now. Molecular clouds are the birthplace of all stars. Somewhere in the deep, quiet darkness between the stars, enormous clouds of gas and dust drift slowly through space. These are molecular clouds, and within their gentle drifting folds, every star that has ever shone was born. They are the nurseries of the universe, vast, patient, and impossibly serene, holding within them the quiet promise of suns not yet lit. A typical molecular cloud can span hundreds of light years across. These clouds are almost beyond imagining in their size. A single molecular cloud might stretch for hundreds of light years, from one edge to the other, so wide that light itself, traveling at its impossible speed, would take centuries to cross it. And yet, for all their enormity, they drift in near-perfect stillness, vast and unhurried, like slow breath in the dark. Molecular clouds are mostly composed of hydrogen gas and dust. The substance of these great clouds is beautifully simple. Hydrogen, the lightest, oldest, most abundant element in the universe, makes up the vast majority of what they contain. Woven through it are fine grains of dust, tiny particles of carbon and silicate drifting like motes in still air. From this simple mixture, all the complexity of stars and worlds will one day grow. Gravity causes pockets within molecular clouds to begin collapsing. Within the vast stillness of a molecular cloud, something gentle and inevitable begins. Gravity, the quiet force that holds all things together, begins to pull at small, denser pockets of gas and dust. Slowly, almost imperceptibly, these pockets begin to draw inward. There is no urgency, no drama. Just the soft, patient work of gravity, gathering matter toward a center, beginning something new. A collapsing pocket of gas is called a protostellar core. As gravity gathers a pocket of gas and dust inward, that region earns a quiet name, a protostellar core. It is not yet a star, not even close. It is simply a place where the universe has decided to begin. A gentle concentration of matter, slowly tightening, slowly warming, holding within it the long, patient potential of a future sun. The collapse of a protostellar core can take millions of years. There is no rushing this process. The collapse of a protostellar core unfolds across millions of years, timescales so immense they dissolve all sense of hurry. While civilizations rise and fall, while continents drift, while whole species come and go, this quiet cloud of gas simply continues its slow inward journey. The universe is in no hurry, and neither are we. As a protostellar core collapses, it heats up due to compression. As the gas falls inward and the core grows denser, something gentle but inevitable happens. It begins to warm. The compression of gas converts gravitational energy into heat, and the core glows a little brighter, a little warmer with each passing age. It is the same quiet warmth you feel when you hold your hands together, just on a scale almost too vast to imagine. A protostar forms when a collapsing core becomes opaque to its own radiation. There comes a moment, deep in the long collapse, when the core grows dense enough that light can no longer pass freely through it. The core becomes opaque. It traps its own warmth inside. At that moment, scientists say, a protostar is born. It is a quiet threshold, invisible to any eye, but it marks the beginning of something that will one day shine. Young protostars are surrounded by a rotating disk of gas and dust. Around the newborn protostar, the remaining gas and dust does not fall straight inward. Instead, it flattens and begins to spin, forming a wide, gently rotating disk that encircles the young star like a slow, graceful ring. This disk turns quietly, in the dark, patient, beautiful, and full of possibility. Within it, one day, planets may form. Let yourself settle now, just a little more deeply. There is nothing you need to hold on to, nothing you need to figure out. Let your shoulders soften, let your jaw release, let your breath move slowly and easily on its own. You are simply here, resting, drifting gently through the quiet dark. Each breath carries you a little further from the day, a little closer to sleep. There is nowhere else to be. The rotating disk of gas and dust surrounding a young protostar is called a protoplanetary disk. This name holds a quiet promise, for within this spinning, flattened ring of material, the seeds of planets are already beginning to gather. Tiny grains of dust slowly collide and cling together, building larger and larger clumps over immense stretches of time. The disk turns in patient silence, unknowingly preparing a world that may one day hold oceans, mountains, and perhaps even life. From the poles of a young protostar, narrow jets of material shoot outward into space. These jets emerge from the very top and bottom of the protostar, launched by powerful magnetic fields threading through the disk below. They are slender, luminous streams of gas moving at tremendous speed, carving their way through the surrounding cloud. Yet even these fierce jets feel somehow graceful from a distance, two thin threads of light reaching quietly into the dark. These twin streams of outflowing material are called bipolar outflows. The name simply describes their shape, two flows, one from each pole, moving in opposite directions away from the young star. Scientists have observed bipolar outflows in star-forming regions throughout the galaxy, glowing softly in radio waves and infrared light. They are a signature of youth, a sign that a new star is still gathering itself, still finding its balance in the great slow turning of the cosmos. Bipolar outflows can extend for light years away from the protostar that launched them. A single light year is nearly 10 trillion kilometers, and yet these jets can reach several light years in length, stretching far beyond the protostar's immediate neighborhood and into the open space of the surrounding cloud. It is a remarkable reach for something so newly born. The outflows push gently into the cloud, like a slow, quiet exhale that spreads and softens as it travels. A protostar's luminosity, the light and energy it gives off, comes entirely from gravitational contraction. There is no fusion happening yet, no nuclear fire burning at the core. All the warmth and glow of a young protostar is simply the energy released as gravity draws the gas inward and compresses it. It is a quiet, ancient kind of energy, the energy of falling, of gathering, of things drawing together. The protostar shines on borrowed time, waiting for something deeper to begin. The Kelvin-Helmholtz mechanism describes the process by which a contracting body releases energy as heat and light. Named for two scientists who studied it in the 19th century, this mechanism explains how a protostar can glow brightly long before nuclear fusion ever begins. As gravity squeezes the gas inward, gravitational potential energy is converted into thermal energy, warmth radiating outward into the surrounding dark. It is one of the universe's most patient and fundamental ways of making light. The very first protostars in the early universe formed from hydrogen and helium alone. When the universe was young, just a few 100 million years old, there were no heavier elements yet. Carbon, oxygen, iron, all the rich complexity of the periodic table had not yet been forged. Those first stars were made of the simplest ingredients, hydrogen and helium, drifting together in the primordial dark, drawn by gravity into the very first points of light the universe had ever known. Modern protostars contain trace amounts of heavier elements, inherited from stars that lived and died long before them. When ancient stars ended their lives, they scattered their ashes, carbon, oxygen, silicon, iron, back into the galaxy. Those elements drifted into molecular clouds, mixing quietly with the hydrogen and helium already there. And so each new star born today carries within it the faint memory of all the stars that came before, a soft inheritance written in atoms. Over time, a protostar gathers more and more mass by pulling in material from the surrounding envelope of gas and dust. This process is called accretion, and it is slow and steady, the protostar quietly drawing nearby material inward, growing heavier and warmer with each passing age. The envelope grows thinner as the protostar grows larger, until one day the supply begins to dwindle. The protostar has taken what it needs, and something new is about to begin. The protostellar phase typically lasts about 100,000 years. In the vast sweep of cosmic time, that is a brief and tender season, a quiet gestation before something truly new emerges. For 100,000 years, the protostar gathers its mass, builds its warmth, and slowly prepares. The surrounding envelope thins, the inner light grows, and then, gently, almost imperceptibly, the phase draws to a close, and the universe moves on to the next quiet chapter. Let your body grow a little heavier now. Let your shoulders settle, your jaw soften, your hands rest open and still. There is nothing to hold on to tonight, nothing to figure out, nothing to remember. Each breath you take moves a little slower, a little deeper, carrying you gently inward. You are warm and safe and held. Let your thoughts drift like slow clouds across a dark and peaceful sky, dissolving one by one into the quiet. As accretion slows and the surrounding envelope thins away, the protostar becomes visible for the very first time as a pre-main sequence star. For so long it was hidden, wrapped in its cocoon of gas and dust. But now the veil lifts, and the young star shines openly into space. It is not yet fully formed, not yet burning hydrogen in its core, but it glows with its own warm light, a new presence, quiet and luminous, settling into its place among the stars. Astronomers use a beautiful map called the Hertzsprung-Russell diagram to chart the lives of stars by their temperature and luminosity. Pre-main sequence stars appear plotted above the main sequence on this diagram, brighter than a mature star of the same temperature would be. They sit there like young travelers who have not yet found their steady path, glowing a little too brightly, still settling into the long and patient rhythm of their lives. The diagram holds their story in a single quiet point of light. For stars of lower mass, stars like our own sun once was, the pre-main sequence phase takes the form of what astronomers call a T Tauri star, named for a young star discovered in the constellation Taurus. T Tauri stars are the early youth of sun-like stars. They are still contracting, still finding their balance, still surrounded by the remnants of the disk from which they formed. They are young in every sense, energetic, unsettled, and full of the quiet potential of things not yet complete. T Tauri stars are known for being highly variable in their brightness and for carrying strong, tangled magnetic fields across their surfaces. Their light fluctuates gently over days and weeks, rising and falling in soft waves as magnetic activity stirs across the stellar surface. Spots and flares come and go, much like weather on a young and restless world. It is a kind of growing up, the star working through its early turbulence before settling into the long, steady calm of its mature life. For stars of intermediate mass, those between roughly 2 and 8 times the mass of our Sun, the pre-main sequence phase is known as the Urbig A, or Bay star phase. These stars are somewhat larger and hotter than T Tauri stars, glowing with a cooler blue-white light. They too are still surrounded by disks of gas and dust, still contracting toward their eventual equilibrium. They are the middle children of the pre-main sequence family, quieter than the most massive young stars, but more luminous than the sun-like ones. As pre-main sequence stars contract, they follow a path on the Hertzsprung-Russell diagram known as the Hayashi track. This track describes the route, a young star takes as gravity slowly squeezes it inward, its properties shifting in a gradual and orderly way. The Hayashi track is like a quiet road through an early landscape, the star traveling along it steadily, without rush, moving toward the place where it will one day settle and begin the long work of its life. Each step along the track is one step closer to becoming a true star. The Hayashi track runs nearly vertically on the Hertzsprung-Russell diagram, which means something gentle and precise as the star descends along it. Its luminosity gradually decreases while its surface temperature remains nearly the same. The star is quietly dimming as it contracts, not cooling, just settling, becoming more compact and more focused. It is like a flame being carefully turned down, its warmth unchanged, its brightness softening into something more sustained. The star is learning, in its slow way, to shine with less. More massive pre-main sequence stars do not follow the Hayashi track for long. Instead, they move along a different path called the Hini track, which runs more horizontally across the Hertzsprung-Russell diagram. Along this track, the star's luminosity stays roughly constant while its temperature rises. These heavier young stars heat up more quickly, moving toward their ignition point along a different, flatter road. Each star, it seems, finds its own quiet way to the same destination, the long, steady, burning life that awaits on the main sequence. The core temperature must reach about 10 million Kelvin to ignite hydrogen fusion. That number, 10 million Kelvin, is the quiet threshold, the whispered password that unlocks a star's true life. Deep inside the contracting core, the heat and pressure have been building patiently for thousands upon thousands of years. And then, at last, the conditions are just right. Hydrogen nuclei begin to merge, and for the first time, the star is making its own light from within. When hydrogen fusion begins, the star reaches what astronomers call the zero age, main sequence. It is a quiet arrival, no fanfare, no sudden flash, just the steady, even glow of a balance finally found. The outward pressure of fusion now gently pushes back against the inward pull of gravity, and the star settles into a long, unhurried equilibrium. Two great forces, perfectly matched, holding each other in a kind of still and endless conversation. Let yourself settle now, just as a star settles into its quiet balance. Feel the weight of the day releasing from your shoulders, your arms, the small of your back. There is nothing left to carry tonight. Let your breath come slowly and easily, in and out, soft as starlight crossing a vast and empty sky. You are already drifting. Let each thought loosen and float gently away, like dust dispersing in the dark between the stars. The zero-age main sequence marks the official birth of a true star. Before this moment, the object was a protostar, then a pre-main sequence star, always becoming, always on its way. But now it has arrived. The zero-age main sequence is the starting line, the first breath, the moment the star earns its name. It will spend the longest and most stable portion of its entire existence here, quietly burning, quietly shining, in a slow and steady rhythm that can last for billions of years. Our Sun reached the zero-age main sequence about 4.6 billion years ago. That is a number almost too large to hold. 4.6 billion years of quiet burning, of steady light pouring outward into space. Long before our planet had oceans, long before the first living thing stirred in ancient waters, the Sun had already begun its patient work. And it has been shining ever since, without interruption, warming everything that orbits it in its gentle, unhurried way. Main sequence stars fuse hydrogen into helium through a process called the proton chain. In this process, pairs of hydrogen nuclei, single protons, slowly combine, step by gentle step, until they form a helium nucleus. Each step releases a small breath of energy, and those small breaths, multiplied countless times every second, become the steady warmth and light of a star. It is one of the most fundamental processes in the universe, patient, repetitive, and quietly beautiful in its simplicity. More massive stars fuse hydrogen through a different process entirely, known as the no cycle. Where the proton-proton chain is a slow, careful merging of pairs, the no cycle moves with a little more energy, suited to the hotter, denser cores of larger stars. These heavier stars burn brighter and faster, their interiors running at higher temperatures that favor a more vigorous pathway. The universe, it seems, offers different roads to the same destination, light and warmth released from the heart of a star. The no cycle uses carbon, nitrogen, and oxygen as catalysts, meaning these elements participate in the fusion reactions, but are neither created nor destroyed by them. They act as quiet helpers, facilitating the joining of hydrogen nuclei without being consumed in the process. Carbon begins the cycle. Nitrogen and oxygen play their roles in turn, and then carbon is restored again, ready to begin once more. It is a loop, endlessly repeating, a soft and elegant cycle written into the physics of the universe. The proton-proton chain dominates in stars below about 1.3 solar masses, stars like our own Sun, and all the smaller, quieter stars scattered across the galaxy. These are the most common stars in the universe, and they all burn by this same patient process, combining hydrogen nuclei one careful step at a time. There is something quietly reassuring in that the most common stars, the most ordinary ones, burn by the gentlest, most methodical of all the fusion pathways. Main sequence stars spend about 90% of their total lifetimes fusing hydrogen in their cores. 9/10 of a star's entire existence is this one long, steady phase, burning hydrogen, holding its balance, shining with quiet constancy. The main sequence is not a brief chapter, but the whole long body of the story. Everything before it was a slow beginning, and everything after will come in its own time. But for now, for most of a star's life, there is only this, the deep, unhurried work of shining. A star's main sequence lifetime is inversely proportional to roughly the square of its mass. The more massive a star, the faster it burns through its fuel, and not just a little faster, but dramatically so. Double a star's mass, and its lifetime shrinks by something close to a factor of 4. This relationship is one of the quiet ironies woven into stellar physics. The stars born with the most fuel are also the ones that spend it most extravagantly, living brilliant but brief lives against the long, slow dark. The Sun's total main sequence lifetime is about 10 billion years. 10 billion years, a number so large it dissolves into something almost dreamlike when you try to hold it. Our Sun has already lived about 4.6 billion of those years, burning steadily and patiently, and it has roughly another 5 billion years ahead of it. That is a vast, unhurried span of time, longer than anything the human mind can truly picture. The Sun is, in every sense, a star in the quiet middle of its life. A star 10 times the Sun's mass lives only about 30 million years on the main sequence. 30 million years sounds immense by human measure, but set against the Sun's 10 billion, it is a brief and brilliant flare. These massive stars burn with such ferocity that they consume their hydrogen at an astonishing rate, spending in 30 million years what the Sun will take 300 times longer to use. They are the shooting stars of the stellar world, vivid, luminous, and gone. Let yourself settle a little more deeply now. There is nothing you need to hold on to, nothing you need to figure out. Let your thoughts become like slow, drifting clouds, not chased away, just allowed to pass. Feel the weight of your body resting, fully supported, fully still. Each breath comes and goes on its own, easy and quiet. You are somewhere soft and safe, and the only thing asked of you right now is simply to rest. The most massive stars can exhaust their core hydrogen in just a few million years. a few million years, and then the long, steady phase of hydrogen burning is already over. These stars, many times more massive than our Sun, pour energy outward with such intensity that their fuel is spent almost before the universe has had time to notice them. They are born blazing, and they burn fast. Their main sequence lives a brief, luminous breath compared to the slow, long lives of smaller stars. Low-mass red dwarf stars can remain on the main sequence for trillions of years. Trillions, a number so far beyond the current age of the universe that no red dwarf has yet had time to leave the main sequence at all. These small, dim stars burn their hydrogen so carefully and so slowly that they will still be quietly glowing long after every larger star in the galaxy has faded. They are the most patient things in the cosmos, burning softly in the dark for longer than the mind can follow. Hydrostatic equilibrium keeps a main sequence star stable against collapse. It is a balance, a continuous invisible negotiation between the inward pull of gravity and the outward push of the energy released by fusion. Gravity wants to compress the star. The energy from the burning core pushes back. Neither force wins. They hold each other in a perfect, sustained stillness that can last for billions of years. It is one of the most enduring balances in all of nature, a quiet standoff that keeps a star shining. Radiation pressure and gas pressure together balance gravity in a main sequence star. These two outward forces work side by side, gas pressure from the sheer heat and motion of particles, and radiation pressure from the torrent of light and energy streaming outward from the core. Together they hold the star open against its own immense weight. It is a kind of teamwork written into the physics of light and matter, a collaboration that has been quietly ongoing in our Sun for 4.5 billion years. The luminosity of a main sequence star scales approximately with the cube or fourth power of its mass. This means that even a modest increase in mass leads to a dramatic increase in brightness. A star twice as massive as the Sun does not simply shine twice as brightly, it shines closer to 8 or 16 times as brightly. The universe amplifies mass into light with remarkable generosity. The relationship is steep and elegant, a quiet mathematical truth that holds across the vast population of stars scattered through the galaxy. The Sun converts about 600 million tons of hydrogen into helium every second. Every single second, without pause, without variation, 600 million tons transformed deep inside that quiet golden sphere above us. And yet the Sun is so vast that this extraordinary consumption barely diminishes it on any time scale we can feel. It has been doing this since long before the Earth existed, and it will continue long after this night, this breath, this moment of rest. The Sun burns on, steady and generous, while you drift softly toward sleep. Each proton-proton chain reaction converts a small fraction of mass into energy via E equals mc squared. The fraction is almost unimaginably small. Only about 0.7% of the mass involved is transformed. Yet because the speed of light is so vast, even that tiny sliver of mass releases an extraordinary flood of energy. It is one of the most efficient natural processes in the universe, quietly humming away in the Sun's core with every passing second, turning the smallest whisper of matter into the warmth that reaches you now. Neutrinos carry away about 2% of the energy produced in the proton-proton chain. Neutrinos are almost nothing at all, particles so light and so indifferent to matter that they pass through the entire body of the Sun in an instant, and through the Earth just as easily. Right now, trillions of them are streaming silently through you without leaving any trace. They carry their small share of the Sun's energy outward into the universe, quiet and invisible, like whispers dissolving into the dark. The solar neutrino problem was resolved by discovering neutrino oscillation. For decades, scientists detected far fewer neutrinos from the Sun than their models predicted, and the discrepancy was quietly puzzling. Then it was understood that neutrinos shift between different types as they travel. They oscillate, changing their identity on the journey. The missing neutrinos had not disappeared. They had simply transformed into forms the early detectors could not see. It was a gentle resolution to a long mystery, a reminder that nature sometimes hides its answers in plain sight. The core of the Sun is about 15 million degrees Celsius. 15 million degrees, a number so far beyond ordinary experience that it dissolves into pure abstraction, something to be held gently rather than truly imagined. At that temperature, matter exists in a state unlike anything on Earth, a dense plasma where particles move with extraordinary energy. And yet from here, from this quiet moment, the Sun's core feels only like warmth, softened by 93 million miles of space into something gentle enough to rest beneath. Let yourself rest now. There is nothing to hold on to, nothing to figure out. Let your breath slow just a little, in and out. Feel the weight of your body settle, each muscle releasing, each thought growing softer and more distant. The facts and the figures, the vast distances and the ancient light, let them all drift gently away, like embers rising from a quiet fire. You are here, you are still, and sleep is very close. Simply let go and let it come. Energy moves outward from the core by radiation in the radiative zone. In this deep inner layer, energy does not flow like water. It travels as light, as photons, each one carrying a tiny parcel of the Sun's warmth. The photons do not move freely, though. They are absorbed and re-emitted, over and over, by the dense plasma surrounding them. Progress is slow and wandering, a patient diffusion of light through matter. The energy makes its way outward in a kind of unhurried drift, step by quiet step. The radiative zone of the Sun extends from the core to about 70% of the solar radius. It is a vast region, more than 400,000 kilometers deep, through which every photon born in the core must slowly wander. It occupies the great quiet interior of the Sun, a place of immense pressure and steady, diffuse warmth. Nothing about it is hurried. The radiative zone simply holds the energy, passing it along in its own unhurried way, layer by patient layer, toward the surface far above. A photon can take over 100,000 years to random walk from the Sun's core to its surface. Born in a fusion reaction, a single photon is absorbed and re-emitted so many times, bouncing in every direction, never moving in a straight line, that its journey to the surface takes longer than recorded human history. The same light that warms your face this morning may have begun its outward journey before our earliest ancestors left any trace. It is a humbling thought, held softly, ancient light finally arriving. The convection zone lies above the radiative zone and carries energy by convective motion. Here the plasma becomes cooler and less transparent, and radiation can no longer carry the energy efficiently. So the Sun finds another way. Great columns of hot plasma rise toward the surface, release their heat, cool, and sink back down again. It is a slow, rolling circulation, like the gentle movement of warm air above a hearthstone. The convection zone is the Sun's outermost layer of churning, and it brings the energy, the final distance, to the light we see. Granulation on the Sun's surface is caused by convective cells rising and falling. Each granule is a single convective cell, a column of hot plasma rising at its bright center, spreading outward, cooling and sinking at its darker edges. Together, they tile the entire visible surface of the Sun in a shifting cellular pattern of light and shadow. From a distance, they look almost like the texture of something organic, something breathing. The Sun's surface is never still. It ripples and refreshes itself continuously, a slow, living texture of warmth. Each granule on the Sun's surface is roughly the size of Texas, That means every single one of those softly glowing cells, rising, spreading, cooling, and sinking, spans about 1,000 kilometers from edge to edge. There are millions of them covering the sun's entire surface at any given moment. Each one is enormous by any earthly measure, and yet from a distance they blend into a single warm, shimmering texture. It is a gentle reminder of how scale dissolves when we look at something as vast and patient as the sun. As hydrogen depletes in the core slowly contracts and heats. After billions of years of steady fusion, the supply of hydrogen at the very center begins to thin. With less fuel to sustain the outward pressure, the core responds the only way it can. It gradually settles inward under gravity's quiet pull. As it contracts, the material compresses, and compression brings warmth. The core grows a little denser, a little hotter, slowly and steadily, a long, unhurried shift that will take millions of years to unfold. The increasing core temperature causes the outer layers of the star to expand. The extra heat radiating outward from the contracting core pushes against the star's outer envelope, and those outer layers begin to respond, slowly, gently drifting outward. The star does not burst or rush. It simply grows, the way a slow breath fills a room. Over millions of years, the outer layers swell away from the center, reaching farther into the surrounding space, the star quietly becoming something larger than it was. This expansion and cooling of outer layers causes the star to become a subgiant. As the outer layers spread outward, they also cool. The same energy now spread across a larger surface, like embers spread thin. The star grows somewhat dimmer in color at its edges, shifting from the steady white gold of its main sequence life toward something softer and warmer. Astronomers call this the subgiant phase, a quiet in-between, neither the stable star it was nor the great red giant it is slowly becoming. A gentle transition measured in millions of years. The subgiant phase marks the star's departure from the main sequence. For most of its life, the star existed in a kind of steady balance, hydrogen burning in the core, light and gravity in quiet agreement. The subgiant phase is where that long equilibrium gently ends. The star has used what it had at its center, and now it begins to change in ways it never did before. It is not a dramatic ending. It is more like the turning of a season, slow and inevitable, the first soft sign that something new is beginning. Let your body soften now, just a little more. If there is any tension still resting in your shoulders, your hands, your jaw, let it go gently, like a breath released into open air. You do not need to hold anything right now. There is nothing to remember, nothing to decide. Simply let yourself be still and quiet, drifting slowly in the warmth of this moment. The universe is patient, and so are you. Let each thought pass through softly, and let your breath slow to its own natural rhythm, easy and unhurried. On the Hertzsprung-Russell diagram, the star moves off the main sequence toward the red giant branch. The Hertzsprung-Russell diagram is a map of stars, plotting their brightness against their temperature, and every star traces a path across it as it ages. For billions of years, our star sat quietly on the main sequence, a stable point of warm light. Now it begins to drift, slowly, steadily, toward the upper right of the diagram, toward the realm of cooler, larger, more luminous stars. It is a quiet migration, written in light. The hydrogen-burning shell ignites around the exhausted helium core. With the core no longer fusing hydrogen at its center, fusion does not simply stop, it retreats. A thin shell of hydrogen just outside the now quiet core finds itself compressed and heated enough to begin fusing on its own. Like a slow ring of warmth encircling a cooling center, this shell quietly ignites and takes over the work of energy production. The core rests, dense and still, while the shell around it burns with patient, steady light. Shell hydrogen burning causes the star's luminosity to increase dramatically. As the hydrogen shell burns, it releases energy more efficiently than the old core fusion did, and the star responds by growing brighter. Over thousands of years, its light output rises, slowly but unmistakably. The star that once burned with steady, quiet constancy now begins to pour more energy outward, its glow deepening and broadening. It is not a sudden flare, it is a long, gradual brightening, like a lamp slowly turned higher in a quiet room. The star's outer radius can expand to tens or hundreds of times its original size. Driven by the energy pouring from the hydrogen-burning shell, the outer layers of the star swell outward over millions of years, reaching distances almost impossible to imagine. A star that was once a compact, steady point of light becomes something immense and diffuse, a great, slow sphere of warm gas, its edges barely held together. Where the star once ended, there is now only a vast, thin atmosphere drifting gently into the space around it. As the star expands, its outer atmosphere cools and spreads wide, and it becomes what we call a red giant. The surface temperature drops, no longer the bright white gold of a younger star, but a deep, warm amber and rust, like embers glowing in a hearth at the end of a long evening. The star is vast now, luminous and slow, its atmosphere so extended that it is more like a great cloud than a sharp surface. It drifts through space in quiet, enormous beauty. Our own sun will one day follow this same path, becoming a red giant in about 5 billion years. That is a span of time so immense it dissolves into pure abstraction. 5 billion years of quiet tomorrows, each one unfolding slowly into the next. The sun today is steady and familiar, a constant companion to our small world, but far in the future it will swell and deepen in color, its light shifting from gold to amber, aging gracefully across an unimaginable stretch of time. When the sun swells into a red giant, its outer layers may expand far enough to reach the inner planets, Mercury, Venus, and perhaps even Earth. Scientists believe the sun's expanding envelope could engulf these worlds, drawing them slowly into its warm, diffuse outer atmosphere. It is not a violent end. It is a slow, unhurried embrace, the star gradually reclaiming the space around it. Whatever remains of those worlds will dissolve gently back into the light from which they came. While the outer layers of a red giant expand and cool deep inside, the core follows a very different path. The helium core, no longer producing energy through fusion, continues to contract under its own gravity, growing smaller and denser and hotter with each passing millennium. At the same time, the hydrogen-burning shell above it pours energy outward. The core and the outer layers move in opposite directions, one compressing inward, one swelling outward, held in a slow, quiet tension. In low-mass stars, a remarkable moment arrives when the helium core has grown hot and dense enough to ignite, and it does so all at once in what scientists call the helium flash. Because the core is so dense that it behaves unlike ordinary gas, the ignition runs away briefly before the core can expand and regulate itself. In a matter of seconds, an enormous amount of energy is released, a flash of fusion deep within the star, silent and sudden, like a breath held and then released. Despite releasing as much energy in a few seconds as the sun produces in 100 million years, the helium flash is never seen from the outside. All that energy is absorbed by the layers of the star above the core, swallowed quietly into the vast surrounding gas before it can reach the surface. To any observer watching from afar, nothing changes. The star simply continues to glow, warm and steady, with no hint of the extraordinary event unfolding silently within. Let yourself rest here for a moment. There is nothing to follow, nothing to hold on to. Let your breath slow, just a little slower with each exhale. Let the weight of your body soften into the surface beneath you. Your thoughts may still be moving, and that is perfectly fine. Simply let them drift past, like slow clouds crossing a dark and quiet sky. You do not need to do anything at all. You are already exactly where you need to be. Let yourself grow still. After the helium flash, the star finds a new equilibrium. The core expands slightly, cools just enough, and helium fusion settles into a steady, controlled burn. The star moves to a region of the Hertzsprung, Russell diagram called the horizontal branch, a quieter, more stable place than the turbulent red giant branch it just left. It is as though the star, after a moment of inner upheaval, has found its footing again, settling into a new rhythm, calm and measured, burning with renewed steadiness. On the horizontal branch, the star burns helium in its core with quiet, steady regularity. This is a second main sequence of sorts, not hydrogen this time, but helium, fusing patiently at the center of the star for tens or hundreds of millions of years. The star is smaller and less swollen than it was as a red giant, its light more controlled and even. It rests in this phase like a traveler pausing at a waypoint, not at the end of the journey, but settled, for now, in a place of calm. Inside the core of a horizontal branch star, helium fuses into carbon through a process called the triple alpha process. 3 helium nuclei, each called an alpha particle, come together in a precise and delicate sequence, first forming an unstable intermediate, then merging with a third to create a carbon nucleus. It is one of the most intricate dances in all of nuclear physics, requiring just the right conditions to proceed, and yet it happens continuously, quietly, in the hearts of countless stars across the universe. The triple alpha process requires temperatures above 100 million Kelvin to proceed. That is a staggering heat, far greater than the temperatures needed to fuse hydrogen, and yet it unfolds with quiet necessity deep inside the star's core. At those extremes, helium nuclei move fast enough and press close enough together to overcome their natural repulsion. The process is precise, almost fragile in its requirements, and yet the universe arranges these conditions with remarkable regularity in star after star across all of time. Carbon, once formed in the stellar core, can fuse with yet another helium nucleus to create oxygen. This second step follows naturally from the triple alpha process as a freshly made carbon nucleus captures an additional alpha particle and transforms. In this way, the red giant's core slowly fills with both carbon and oxygen, built atom by atom in the deep quiet of nuclear fire. 2 of the most essential elements in the universe are born together, side by side, in the heart of a dying star. The exact ratio of carbon to oxygen produced in a red giant core is not fixed. It depends sensitively on the rates of the nuclear reactions involved. If the reaction that builds oxygen proceeds quickly, more oxygen accumulates. If it runs slowly, carbon dominates. Scientists study these reaction rates carefully because the balance between carbon and oxygen shapes the entire future of the star. It is a quiet negotiation happening deep inside, invisible and unhurried, determining what the star will leave behind when it is gone. When the helium in the core is finally exhausted, the star begins to swell once more, ascending what astronomers call the asymptotic giant branch. The core, now composed of carbon and oxygen, contracts and heats, while the outer layers expand outward again into enormous luminous clouds of gas. The star grows larger and brighter than it was even as a red giant, drifting upward on the diagram of stellar life toward a region of extraordinary size and glow. It is the star's last great expansion, slow, vast, and inevitable. Stars on the asymptotic giant branch carry 2 burning shells within them, one fusing hydrogen, one fusing helium, layered around an inert carbon-oxygen core. These two shells sit one above the other, like nested rings of slow fire, each feeding energy outward through the star's vast envelope. It is a more complex arrangement than anything the star has known before, two simultaneous processes sustaining its enormous luminosity. The star is working harder now, burning on two fronts at once, deep in the long last chapter of its life. The two burning shells inside an asymptotic giant branch star do not simply burn in steady silence, they interact with one another, producing dramatic events called thermal pulses. Periodically, helium builds up beneath the hydrogen-burning shell until it ignites in a sudden rush, sending a wave of energy outward through the star. These pulses repeat on timescales of thousands to tens of thousands of years, each one a slow, deep breath of the star, a rhythmic stirring far below the surface, felt across the entire enormous body of the star. Each thermal pulse causes the asymptotic giant branch star to pulsate, its outer layers swelling and contracting in a slow, deep rhythm. With each pulsation, the star sheds mass, blowing streams of gas and dust outward into the space around it. Over thousands of years, this steady shedding carries away a significant portion of the star's outer envelope, releasing it gently into the surrounding interstellar medium. The star is slowly, quietly giving itself back to the universe, breath by breath, pulse by pulse, in a long and unhurried release. Let yourself grow softer now. There is no need to hold on to anything, not a thought, not a worry, not a single word from this quiet journey through the stars. Simply let your body settle, heavy and still, into the warmth beneath you. Let your breath come and go on its own, slow and easy, without any effort at all. You are resting now. The stars are far away and peaceful, and so are you. Let everything grow quiet. Let yourself drift. Asymptotic giant branch stars are among the most luminous stars in an entire galaxy. In their final swollen phase, they can shine with the light of thousands or even tens of thousands of suns, blazing with a warm, deep radiance visible across enormous distances. Despite their great brightness, they burn with a slow, cool glow, red and amber and deep orange, vast and unhurried. They are giants in every sense, enormous and luminous, moving through the final stages of their lives with a quiet, almost serene magnificence. As an asymptotic giant branch star pulsates and sheds mass, it drives powerful stellar winds that blow its outer envelope away into space. These winds are not violent gusts but slow, steady streams, carrying gas and dust outward at tens of kilometers per second, over thousands and thousands of years. Gradually, the star's vast outer layers are stripped away, dispersed into a growing cloud of material surrounding the star. The envelope thins and fades, and what remains at the center grows ever more exposed, a hot, dense core, quietly waiting. Asymptotic giant branch stars are among the great forges of the universe, producing carbon and heavy elements through a process called the S process. Deep within their layered interiors, these stars quietly build atoms heavier than iron, weaving them together one neutron at a time. The elements created here, barium, strontium, lead, and others, will eventually drift out into space, becoming part of new stars and new worlds. These vast, glowing stars are quietly enriching the universe with each slow breath they take. The S process builds heavy elements through slow neutron capture, a patient, unhurried process unfolding deep inside the star. Atomic nuclei absorb neutrons one at a time, slowly accumulating mass and transforming into heavier and heavier elements over long stretches of time. The word slow here is relative. Each capture may take years or centuries, but in the deep interior of a star, time moves at its own quiet pace. Element by element, atom by atom, the universe grows richer and more complex. Periodically, deep convective currents rise through the asymptotic giant branch star in events astronomers call dredge-ups. These slow, rolling motions carry newly forged heavy elements from the deep interior upward toward the star's outer layers, mixing them gently into the stellar atmosphere, like a slow current rising through still water. These dredge-up events bring the hidden work of the interior to the surface. The star carries its own creations upward, preparing to release them into the universe when the time comes. Some asymptotic giant branch stars, after repeated dredge-up events, become what astronomers call carbon stars. Their outer atmospheres grow so enriched with carbon that carbon outnumbers oxygen, a reversal of the usual balance found in most stars. This gives carbon stars a distinctly warm, deep reddish hue, their light filtered through clouds of carbon-bearing molecules drifting in their extended atmospheres. They glow with a deep, rich warmth, quiet and ancient, their surfaces telling the story of everything forged within. Among the most gently rhythmic of all stars are the Mira variables, pulsating asymptotic giant branch stars whose brightness rises and falls over periods of hundreds of days. Named for the star Mira in the constellation Cetus, these stars breathe in and out over cycles lasting 300, 400, even 600 days or more. Their light swells and fades in a slow, patient rhythm, a long, deep heartbeat stretching across the months. To watch a Mira variable is to watch a star breathing quietly in its sleep. As an asymptotic giant branch star sheds mass over thousands of years, the expelled material does not simply vanish. It gathers into a wide, softly glowing shell surrounding the star, called a circumstellar envelope. This envelope is made of gas and dust, slowly drifting outward in all directions, growing larger and more diffuse with time. It is a quiet, expanding cloud, a soft record of everything the star has given away. Seen from a great distance, it wraps the star in a pale, luminous haze, like a lantern held inside a veil of smoke. When an asymptotic giant branch star has shed most of its outer envelope, it enters a new and quieter phase, the post-asymptotic giant branch stage. The vast swollen atmosphere is mostly gone now, dispersed into the surrounding space over thousands of years of slow winds and gentle pulsations. What remains is a smaller, denser, hotter object, the exposed remnant of the stellar interior, no longer hidden beneath layers of cool gas. The star has shed its outer self and stands revealed, moving quietly toward its final transformation. Post-asymptotic giant branch stars move across the Hertzsprung, Russell diagram with surprising swiftness, at least by stellar standards. As the remaining envelope thins away, the star's surface temperature rises rapidly, shifting from the cool reds and oranges of its giant phase toward the brilliant blues and whites of a much hotter object. This crossing can take only a few thousand years, a brief flicker in the long life of a star. On the diagram, the star traces a swift, quiet arc, moving steadily toward the upper left, growing hotter and more luminous with each passing century. Let your breath slow now, soft and even. There is nothing to follow, nothing to hold, nothing that needs your attention. Feel the weight of your body, heavy and still, resting completely. Let your thoughts grow distant, like stars very far away, faint and quiet and unhurried. You are warm. You are safe. Everything is calm and slow. There is only this gentle darkness, and the quiet and the slow rise and fall of your breath. Let yourself drift a little further now. Let go. As the post-asymptotic giant branch star grows hotter, it begins to emit powerful ultraviolet radiation, and this radiation reaches the surrounding shell of expelled gas that the star shed during its giant phase. The ultraviolet light strips electrons from the atoms in the gas, ionizing them, causing the entire shell to begin to glow. What was once a cold, dark cloud of drifting material now lights up from within, illuminated by the radiation of the star at its center. A new kind of beauty is quietly beginning to bloom in the space around the dying star. The ionized gas shell, glows as a planetary nebula, one of the most quietly beautiful sights in the known universe. As electrons recombine with their atoms, they release light in soft waves of color, blues and greens and gentle pinks, spreading outward in great luminous rings. The shell does not flash or burst. It simply glows, steadily and peacefully, like a lantern held up in the dark. For tens of thousands of years, this soft radiance drifts outward through the stillness of space. The name planetary nebula is a historical misnomer, born from the limits of early telescopes. When astronomers in the 18th century first glimpsed these glowing shells, they appeared round and faintly colored, not unlike the distant disks of Uranus and Neptune. William Herschel, who first used the term, had no way of knowing they were dying stars rather than distant worlds. The name stayed, a gentle reminder that even careful observers sometimes see what they expect to see. Planetary nebulae come in many shapes, rings, bipolar lobes, spirals, and irregular forms that drift and billow like slow breath made visible. Some appear as perfect glowing rings, others as twin lobes reaching outward in opposite directions like wings spread wide and still. Some are asymmetric, shaped by winds and rotation into forms that have no easy name. Each one is unique, a quiet signature of the star that made it, written in light across the dark. Magnetic fields and binary companions influence the shape of planetary nebulae in ways scientists are still gently unraveling. A companion star nearby can tug and twist the outflowing gas, sculpting it into lobes or spirals rather than simple spheres. Magnetic fields threading through the stellar wind can collimate the flow, guiding material along invisible lines. The result is that no two planetary nebulae are quite alike, each shaped by its own quiet history, its own unseen companions and forces. The central star of a planetary nebula eventually becomes a white dwarf, the quiet, dense remnant left behind when the glowing shell has drifted too far away to be seen. As the nebula slowly fades and disperses into the surrounding space over tens of thousands of years, the central star grows dimmer and cooler, no longer illuminating the gas that once surrounded it. What remains is a small, dense, faintly glowing point of light, the final, still form of what was once a living star. White dwarfs are supported by electron degeneracy pressure, not by fusion, not by heat, but by a quiet force rooted in the nature of matter itself. When electrons are compressed close enough together, the laws of quantum mechanics prevent them from occupying the same state, and this resistance pushes back against gravity. No burning is needed. No fuel is consumed. The white dwarf simply holds itself up through the stubbornness of its own electrons, resting in a kind of permanent, peaceful stillness. A white dwarf is roughly the size of Earth, and yet it contains about half a solar mass, the compressed remnant of a star that was once vastly larger. If you could hold a teaspoon of white dwarf material, it would weigh as much as a small car. All of that mass, once spread across a giant star, hundreds of times the size of our Sun, now rests quietly within a sphere, no wider than our own small planet. It is one of the gentlest demonstrations of how much empty space ordinary matter contains. The density of a white dwarf is about 1 million times that of water, a number that is almost too large to hold gently in the mind. Ordinary matter, the kind that makes up everything around us, is mostly empty space between electrons and nuclei. In a white dwarf, that space has been pressed away. The electrons and nuclei are packed as closely as quantum mechanics will allow, creating a substance of extraordinary stillness and weight. It is matter at rest, compressed into its most compact, peaceful form. White dwarfs cool slowly over billions of years, fading from white to yellow to red, their light dimming so gradually that the change is imperceptible across a human lifetime. With no fusion to generate heat, a white dwarf simply radiates the warmth it already holds, releasing it quietly into the surrounding dark. Over hundreds of billions of years, it will grow cooler and dimmer, shifting through softer and softer colors. It is one of the slowest, most patient processes in the universe, a long, unhurried fading into rest. Let yourself settle now, just a little more. There is nothing to hold on to, nothing to figure out. Feel the weight of your body resting completely, sinking softly into stillness. Your breath is slow and even. Your thoughts, if they come, can drift past like distant light, quiet and unhurried. You are here and you are safe, and the night is very still around you. There is nothing more to do now. Just rest. Just breathe. Let yourself go gently, slowly, into the soft and welcoming dark. The coolest theoretical end state of a white dwarf is a black dwarf, a cold, dark, inert sphere that no longer emits any light at all. No black dwarfs exist yet anywhere in the universe. The cosmos has simply not been around long enough for even the oldest white dwarfs to cool that far. It is an end state that belongs to the future, billions upon billions of years from now, a quiet, patient destination the universe has not yet reached. Stars above, about 8 solar masses, end their lives very differently from the low-mass stars we have been following. Where a star like our Sun will gently exhale its outer layers and settle into a white dwarf, a massive star follows a far more dramatic path. These are the great engines of the cosmos, stars so heavy that gravity never loosens its grip on them, pushing them through stage after stage of burning until something far more profound occurs. Their story is one of deep, relentless transformation. Massive stars develop an onion-like shell structure of fusing elements as they age. Deep in the core, the heaviest elements burn, while progressively lighter elements fuse in shells layered around it, each one sitting above the next, like the layers of a great, slow-burning sphere. Hydrogen still fuses in the outermost shell. Helium burns beneath it. Carbon, then heavier elements, burn in the shells below. It is an architecture of extraordinary order, built quietly over millions of years. After helium burning, massive stars fuse carbon, then neon, then oxygen, then silicon, each new fuel igniting in the core as the previous one is exhausted. Carbon burning begins at temperatures of hundreds of millions of degrees. Neon burning follows, then oxygen, each stage hotter and more compressed than the last. Silicon burning is the final stage before the star reaches a threshold it cannot cross. Each new fire is quieter and shorter than the one before, the star working through its remaining fuel with growing urgency. Silicon burning in a massive star produces an iron core within just a matter of days. Where earlier burning stages lasted millions or thousands of years, silicon burning races to completion with startling speed. The silicon is consumed, and iron accumulates at the very center of the star, building steadily with each passing day. In the span of time, it might take a season to change on Earth. The fate of a star, many times the mass of our Sun, is quietly, irrevocably sealed. Iron cannot release energy through fusion, so the iron core cannot support the star against its own gravity. Every element that burned before iron gave back more energy than it took to ignite, but iron is different. Fusing iron actually consumes energy rather than releasing it. The fire that has sustained the star through millions of years of burning simply stops at iron. There is no next fuel, no next flame. The core grows heavier and heavier, and the force that has held the star open begins to lose its hold. When the iron core exceeds about 1.4 solar masses, it collapses under its own gravity in under a second. The core, which has held its shape for thousands of years, simply gives way all at once. In a fraction of a heartbeat, a sphere roughly the size of Earth compresses down toward the size of a city. It is one of the most sudden and complete transformations in the universe, not a slow fading, but an instantaneous surrender to gravity's oldest and most patient pull. Each successive burning stage in a massive star is shorter than the one before it. Hydrogen burning on the main sequence lasts millions of years. Helium burning lasts hundreds of thousands. Carbon burning takes perhaps 1,000 years. Neon burning lasts about a year. Oxygen burning takes months. Silicon burning is measured in days. The star moves through its final fuels with increasing speed, each chapter shorter and more compressed than the last, until the whole sequence ends almost before it has begun. Core collapse takes less than 1 second and compresses the core to nuclear density, the same extraordinary density found inside the nucleus of an atom. In that single second, a mass greater than our Sun is crushed into a sphere only a few tens of kilometers across. The protons and electrons are forced together into neutrons. The core, which was once a slowly burning stellar heart, becomes something almost unimaginably dense and still. All of that mass, all of that history, compressed into a moment and a point. The collapsing core rebounds when nuclear forces become repulsive, sending a shock wave outward through the infalling material. As the core reaches nuclear density, the strong nuclear force pushes back against further compression. The core bounces. That bounce sends a powerful wave of energy surging outward, a shock wave moving through the star's layers at extraordinary speed. After millions of years of burning and seconds of collapse, the star now carries within it a wave of energy that will change everything around it. Let your body settle a little more deeply now. Feel the weight of your limbs, the softness of where you rest. There is nothing to hold on to, nothing to figure out. Let each breath come and go without effort. Let your thoughts drift like slow clouds across a quiet sky, each one passing gently, leaving only stillness behind. You are safe and you are at rest. Simply let go and let the night carry you. Neutrinos carry away about 99% of the energy released in a core collapse supernova. These tiny, nearly massless particles flood outward from the collapsing core in an almost unimaginable torrent, more energy than the Sun will radiate across its entire 10 billion-year lifetime, released in just a few seconds. Neutrinos pass through almost everything without interaction, and yet in that brief moment, they carry the story of the star's final heartbeat silently out into the universe. The shockwave and neutrino energy blow off the star's outer layers in a core collapse supernova. The shockwave alone would stall as it fights through the dense infalling material, but neutrinos deposit just enough energy to revive it. Together, they drive the star's outer layers outward in an expanding shell of gas and light. Layers that took millions of years to build are gently unraveled in hours, released back into the space from which they once came. A core collapse supernova can briefly outshine an entire galaxy. For a few days or weeks, the light of a single dying star can equal the combined light of hundreds of billions of suns. Seen from across the universe, a galaxy will suddenly flare with a single brilliant point, then slowly fade. It is one of the most luminous events in the cosmos, a quiet, ancient star announcing its end with a light that crosses billions of light years. Supernova 1987. In the Large Magellanic Cloud was visible to the naked eye. On the 23rd of February, 1987, a star in our neighboring galaxy flared bright enough to be seen without a telescope from the southern hemisphere. It was the closest observed supernova in nearly 400 years. People simply looked up and saw it, a new soft point of light that had not been there the night before, glowing quietly in the sky for months. The Rahr process in supernovae creates heavy elements heavier than iron by rapid neutron capture. In the extreme environment of a collapsing star, atomic nuclei are bombarded by neutrons so quickly that they cannot decay before capturing another. In fractions of a second, nuclei are built up into gold, platinum, uranium, and dozens of other heavy elements. The periodic table's heaviest entries are written in the final moments of a dying star, forged in conditions that exist nowhere else. Neutron-star mergers detected by gravitational wave observatories also produce our process elements. When two neutron stars spiral together and collide, they create a brief, extraordinarily violent environment called a kilonova. Scientists believe that a significant portion of the universe's gold and platinum is born in these rare collisions. In 2017, observatories detected both gravitational waves and light from such a merger, a moment when the universe revealed one of its most ancient and quiet secrets. The remnant of a core-collapsed supernova is either a neutron star or a black hole. What remains after the explosion depends on the mass of the collapsing core. If the core is not too heavy, it settles into a neutron star, a dense, quiet object unlike anything else in nature. If the mass is too great, even the neutrons cannot hold, and the remnant collapses further into a black hole. Either way, something entirely new is born from the star's final moment. Neutron stars are about 20 kilometers in diameter, but contain 1 to 2 solar masses. In the span of a small city, a neutron star holds more mass than our entire sun. A single teaspoon of neutron star material would weigh billions of tons on Earth. And yet these objects rest quietly in space, small and still, their surfaces smooth and cool compared to the fire that made them. They are among the densest stable objects the universe allows to exist. Neutron stars are supported by neutron degeneracy pressure. Just as white dwarfs are held up by the resistance of electrons to being compressed, neutron stars are held up by the same quantum principle applied to neutrons. A Pauli exclusion principle forbids two neutrons from occupying the same quantum state, and that resistance is all that stands between a neutron star and total collapse. It is a law written into the fabric of matter itself, quiet, invisible, and utterly dependable. Pulsars are rapidly rotating neutron stars that emit beams of radio waves. As a neutron star spins, it sends out two narrow beams of radio energy from its magnetic poles, much like a cosmic lighthouse sweeping its light across the dark. If one of those beams happens to sweep past Earth with each rotation, we detect a precise rhythmic pulse. The regularity of these pulses is extraordinary, some keeping time more reliably than the finest clocks ever built on Earth. Let the weight of the day dissolve a little more with each breath you take. There is nothing left to solve tonight, nothing left to carry. Simply allow your body to grow heavier and softer, sinking into whatever surface holds you. Let your thoughts slow like clouds drifting apart on a still evening sky. You are safe, you are still, and all is well. Rest is already finding you. The Crab pulsar rotates about 30 times per second and is the remnant of a supernova seen in 1054C. Ancient astronomers across the world recorded a new star blazing in the daytime sky in the year 1054. Nearly 1,000 years later, at the heart of the glowing nebula that explosion left behind, a tiny neutron star still spins, 30 full rotations every single second. It is a quiet testament to how long the universe remembers its own great moments. Millisecond pulsars can spin hundreds of times per second. Some neutron stars, after drawing material from a companion star over long periods of time, are spun up to astonishing speeds, rotating hundreds of times every second. Scientists call these recycled pulsars, and there is something quietly wonderful about that name. An old stellar remnant given new energy by a companion, turning faster and faster in the dark. Even in the universe's late hours, things can be gently renewed. If the collapsing core exceeds about 3 solar masses, not even neutron degeneracy can halt the collapse. There is a limit to what neutrons can withstand when the mass of a collapsing core grows too great, beyond roughly 3 times the mass of our Sun. The quantum pressure that holds neutrons apart is simply overwhelmed. Nothing in the known laws of physics can stop what happens next. The core continues to fall inward, past every boundary nature has set, into something altogether different. A stellar, mass black hole forms when the remnant mass exceeds the Tolman-Oppenheimer-Volkoff limit. This limit, named for the physicists who first calculated it, marks the boundary beyond which no known force can support matter against gravity. When a collapsing stellar core crosses this threshold, it becomes a black hole, a region where gravity has won completely. The Tolman-Oppenheimer-Volkoff limit sits somewhere between about 2 and 3 solar masses, though scientists continue to refine that boundary with each new observation. The event horizon of a stellar black hole is only a few kilometers in radius. For all the immense gravity a stellar black hole commands, its event horizon, the boundary beyond which nothing returns, is remarkably small. A black hole of a few solar masses has an event horizon only about 6 to 18 kilometers across, smaller than a city. And yet that invisible boundary marks one of the most profound edges in the known universe, where the familiar rules of space and time quietly end. Stellar black holes warp space-time so severely that not even light can escape. Einstein's general theory of relativity tells us that mass curves the fabric of space-time, and a black hole curves it so completely that all paths, even the path of light itself, curve back inward. Light that crosses the event horizon does not slow down. It simply has no direction left that leads outward. The universe continues just beyond that boundary, but nothing from within it can ever reach us again. The supernova explosion disperses heavy elements into the surrounding interstellar medium. All the elements forged in the long life of a massive star, carbon, oxygen, silicon, iron, gold, and more, are scattered outward by the force of the supernova. They mix into the vast clouds of gas and dust that drift between the stars. In time, those enriched clouds will collapse again, forming new stars, new planets, new possibilities. The star's ending is not a loss. It is a gift, quietly given to everything that comes after. Supernova remnants like the Crab Nebula expand outward for thousands of years. Long after the star itself is gone, the shell of gas and energy it expelled continues to grow, slowly, steadily, for tens of thousands of years. The Crab Nebula, born from that supernova of 1054, is still expanding today, its delicate filaments reaching a little further into space with every passing century. It is one of the most beautiful things the universe makes, a slow, luminous memory of something that was once a star. Supernova shock waves can trigger the collapse of nearby molecular clouds, forming new stars. When a supernova releases its energy, the expanding wave does not simply fade away. It moves outward through space, and when it reaches a drifting molecular cloud, it gently compresses that cloud, nudging pockets of gas past the threshold of collapse. New protostars begin to form. The ending of one star quietly becomes the beginning of many others, and the cycle turns again, patient and unhurried as ever. Every atom of iron in your blood was forged in the core of a massive star. The iron that flows quietly through you right now was not made on Earth, and it was not made in our sun. It was made long ago, deep inside a star far more massive than our own, in the final burning stages of its life. That star collapsed and scattered itself across space, and eventually those atoms found their way into the world, into life, into you. You carry the memory of a star within you. Let your body grow a little heavier now, sinking softly into wherever you are resting. There is nothing left to do tonight, nowhere to be, nothing to hold on to. Let each breath come a little slower, a little deeper. Let your thoughts drift like dust between the stars, unhurried, weightless, going nowhere in particular. You are safe. You are still. Let the quiet of all that vast and gentle space settle around you now, and simply rest. White dwarfs in binary systems can accrete mass from a companion star and reunite as a type Ia supernova. A white dwarf that has long since gone quiet can have a second story if a companion star drifts close enough. Material from that companion spirals slowly down onto the white dwarf's surface, building up over vast stretches of time. When the accumulated mass pushes the white dwarf past a critical threshold, about 1.4 solar masses, it ignites completely, a final and brilliant blossoming of light. Type Ia supernovae produce large quantities of iron and nickel that enrich the interstellar medium. Because every type Ia supernova occurs at nearly the same critical mass, each one releases a remarkably similar amount of energy and forges a similar abundance of elements. Iron and nickel pour outward into the surrounding space, mingling with the gas and dust of the galaxy. Over billions of years, these contributions accumulate, slowly enriching the raw material from which all future stars and planets and worlds will one day be made. The entire life cycle of stars continuously recycles matter throughout the galaxy, from molecular cloud to protostar, from main sequence to giant, from supernova to nebula, and back again. Nothing is truly lost. The galaxy is a slow, breathing system, turning the same matter over and over across billions of years. The atoms in a star today were once adrift in empty space. The space between stars today holds atoms that were once inside a sun. And somewhere in all of that quiet turning, here you are, made of the same ancient matter, resting now, breathing slowly, part of the same great and gentle cycle. The stars are not distant from you. They are, in a very real sense, what you are made of. Sleep well. The universe continues its slow and patient work, and you can rest now, knowing you belong to something so much larger than any single night. Good night.